In common with most braking systems, aircraft wheel brakes function by using friction between a fixed surface and a moving one to bring an aircraft to rest. In common with most braking systems, aircraft wheel brakes function by using friction between a fixed surface and a moving one to bring an aircraft to rest, converting kinetic energy into heat energy. The amount of heat generated in stopping a large modern aircraft is enormous. The problem of dissipating this heat has been a challenge to aircraft designers and scientists for many years. Braking systems have been improved, but aircraft have got faster and heavier, making heat dissipation a constant problem. The use of reverse pitch on propeller-driven aircraft and reverse thrust on jet-engined aircraft, plus the use of ground spoilers, has helped reduce the work the brakes need to do. But even with these, the need for powerful brakes still exists. In this, the first in a set of 3 lessons on wheel brakes, the components that make up a typical aircraft braking system will be described. All modern aircraft now use plate or disc brakes operated by hydraulic systems as their means of slowing down or stopping. Light aircraft use a very similar system to that used on cars. It consists of a pair of fixed friction pads bearing on or gripping a metal disc, which rotates with the wheel. The friction pads are made of an inorganic material, and the plates are of forged steel, with an especially case-hardened surface. With no pressure applied to the toe brake pedal, the pads are knocked away from the disc by the action of it rotating. If pressure is applied to the toe brake pedal, hydraulic pressure will build up in the slave cylinder behind the piston. This pressure will cause the piston to move over within the caliper unit, pushing the brake pad against the disc. The reaction of the right-hand brake pad pushing against the disc will cause the caliper unit to move in the opposite direction, carrying the left-hand pad with it until the disc is squeezed between the 2 pads. The force applied to the brake pads will be proportional to the effort applied to the toe brake pedal. The toe brake pedals can be applied together, or, if differential braking is required for ground maneuvering, the toe brakes can be used separately. When brake pressure is released, imperfections in the rotating brake disc once again cause the brake pads to move apart, so that the residual braking effect is minimal. On a simple light aircraft system, the pilot is able to apply sufficient pressure to the pedal with his foot to operate the brakes and slow the aircraft down. However, on larger aircraft, the pressure required to operate the brakes is greater than can be generated by the pilot's feet, so aircraft hydraulic system pressure, controlled by metering valves connected to the foot pedals, is used. There will be a primary and an alternate hydraulic source available. The alternate source often has independent pipework. There may also be an accumulator for use in the case of total hydraulic system failure. On large aircraft, the braking surface is increased by using multiple brake plates, known as rotors, sandwiched between layers of friction material mounted on assemblies known as stators. This greatly increases the surface area, thus increasing the braking ability and helping to reduce the brake temperature. In this sort of construction, the rotating brake plates or rotors are key to revolve with the outer rim of the wheel, and the stationary pad assemblies or stators carrying the friction material are key to remain stationary with the axle. The actuating pistons are housed in a fixed torque plate. They push on the sliding pressure plate. The stator and rotor assemblies are fitted between the pressure plate and a fixed thrust plate. When the brake is applied, hydraulic pressure pushes the actuating pistons, squeezing the rotors and stators between the pressure plate and the thrust plate. The harder the brake pedal is pressed, the greater will be the braking force applied to the pressure plate by the pistons. On aircraft with undercarriage bogies, the torque developed during braking will attempt to rotate the bogie about its pivot point. This is prevented by brake torque rods attached to the landing gear leg. Recent technological advancements in heat dissipation have resulted in the design of the brake disc plates being changed from a continuous rotating single plate to a plate constructed of many interconnected individual segments, with the heat dissipation properties being greatly improved, thus increasing brake efficiency. Carbon is now often used for manufacturing brake units because it has much better heat absorbing and dissipating properties than steel. This allows higher levels of braking to be maintained for longer. It also allows for quicker turnarounds, as it is not necessary to wait so long for the brakes to cool before taking off again. Carbon brakes are also much lighter than equivalent steel units. The disadvantages are their increased cost and shorter life. However, the advantages outweigh the disadvantages, and they are now found on most modern aircraft. If, in spite of all of this, the brakes become too hot, they will not be able to absorb any further energy, and their ability to slow down the aircraft rapidly diminishes. This phenomenon is termed brake fade. Each brake unit is fitted with brake adjusters, which use springs to move the pressure plate back when the brakes are released, allowing the stator and rotor assemblies to move slightly apart. The internal construction of the brake adjuster assemblies allows them to maintain a constant running clearance when the brakes are off, thereby automatically compensating for brake wear. The retraction pin is connected to the pressure plate and is a tight fit in the friction bush, which is part of and moves with the guide assembly. When the brakes are released, the spring will pull the guide, the pin, and the pressure plate to the left, allowing the stator and rotor assemblies to move slightly apart. When the brakes are applied, the pressure plate will pull the pin and guide assembly to the right until the guide reaches the end of its travel. If further movement is required because of pad wear, the pin will be pulled through the friction bush. When pressure is released, the spring will pull the guide, pin, and pressure plate back to the left until the guide assembly once again reaches the end of its travel, thus maintaining a constant running clearance. If the return spring inside the adjuster assembly ceases to function, or if the unit is wrongly adjusted, then the brakes may not release fully. This is termed brake drag. Brake drag will generate a lot of heat and can be responsible for brake fade occurring sooner than it otherwise would, or even for a brake fire. It is important that the thickness of the brake lining material is carefully monitored. Too little brake lining material remaining may mean that the disc of a single brake system becomes excessively worn or grooved, or on a multiple disc brake, the remaining material overheats and erodes extremely quickly. On multiple disc brake systems, the most popular method of gauging the depth of brake lining material remaining is by checking the amount that the retraction pin, or the wear indicator pin as it is sometimes called, extends from the spring housing with the brake selected on. The minimum amount that the pin can extend beyond the housing for the brakes to remain in service will be laid down by the manufacturer. On systems where the retraction pin is located inside the housing, a wear gauge can be used to check the distance that the pin has moved within the housing. The wear gauge is held against the housing and the rod is screwed in until it touches the retraction pin. The maximum distance that the rod is permitted to extend will once again be laid down by the manufacturer. An alternative method which can be used, if no retraction pins are fitted to the system, is that, if it is accessible, the amount of clearance between the back of the pressure plate and the brake housing can be measured, again with the brakes applied. The main points to be taken from this lesson are that aircraft brake systems are normally hydraulically operated, and the discs are manufactured from either steel or carbon. Carbon brakes are more efficient and heat up less than steel. However, they are more expensive and wear more quickly. You should understand the problem of brake fade. And finally, you should understand the function of automatic brake wear adjusters and the methods used for indicating wear.